Hello, and here we are, the last video of the first unit. We now have angle measure established, what rotation is, how to measure angles. So now, with the last video we got here, I want us to start looking into how that is used. Angle measure is astoundingly important, and we will look at that very extensively in the next unit, and to a lesser extent in the unit after that. So we will look at it all for the rest of the semester, really. It is tremendously important. It has applications all over the place, not just in mathematics, but in engineering and physics and science and all those other things that people like to do in these courses. So let's get to it. Time to use angle measure. So hold on to these conversions. We'll probably need them here. But I've got a question, and we'll worry about these scary formulas here in a bit. I know that for a circle of radius r, I know how to find circumference, I know how to find area, 2 pi r squared. So how do I find part of the circumference, or part of an area? Let me show you what I mean. So I have this circle, it's of arbitrary radius, I can make it whatever I want. And suppose I want to have half of it. Well then, obviously the circumference is half the full circumference, and the area is half the full area. All right. But what if I wanted to say have, some central angle equal to pi over 6, something like that. So that would be a 30-degree angle right here. How much is my arc length? How much of the circumference do I have, and how much of the area do I have? That's the question I'm asking. So as we move, or as we continue to add on more and more of the circle, or eating up more of that pie there, how much arc length do I have? Or how much area do I have? What's my arc length? What's my sector area? And the way to answer that is actually to start with what we started with here. When I have half of it, right, when I'm doing half the full rotation, I've got half the area. When I'm doing a fourth, I'm sorry, that's an eighth. When I'm doing a fourth of the full rotation, and you'll have to pardon there, I'm getting half that, right? I'm getting a fourth of the area. When I'm doing 1/8 of the rotation, I'm getting 1/8 of the area. So we have a very clear one-to-one correspondence between what percentage of the rotation you're doing, and what percentage of the circumference you have, and what percentage of the area you have. So we have now established ratios. Right, the area of my sector is to theta as the area of the whole circle is to 2 pi, right? Because if I had 2 pi here, I'd have the whole circle. So solving now for the area, I multiply both sides by theta, and 2 pi kind of shows up. I substitute 2 pi r, I'm sorry, not pi r. I substitute pi r squared for the area of the circle. So I got all this stuff. The pi's cancel, and that's pretty much all we get. So this simplifies down to r squared theta over 2. Or maybe easier to remember is just this ratio. Also, the arc length, the amount of the circumference you have after you rotate some amount, is simply, after you clean this up, r theta, which is even easier to remember. So our immediate application is our ability to now find chunks or sections of circles. We can find their arc lengths, we can find their areas, all based on how much we have, all based on the angle of rotation between start and end. Now, one caveat. These theta values, right, these angles have to be in radians. They have to be. And the reason for that is because radians, technically speaking, is a unitless ratio. It doesn't have units. And so, if you look at this from an engineering perspective, if you look at these equations as an engineer, you have arc length equaling r theta. Arc length is in some distance measure, radius is in some distance measure, therefore degrees can't be used. Degrees is a unit, so we have to use radians. By similar extension, right, area is in square units, square meters, square feet, square inches, that sort of thing. Radius, again, is in a distance measure. So I have square units on the left, I have to have square units on the right. Radius already speaks for both of those, so degrees can't be used here. Degrees has a unit. Degrees is a unit. Therefore, radians have to be used for finding sector area and arc length. Which kind of makes sense again because we are looking at ratios and radians are defined in the context of that. So to do one right quick, suppose I had a circle of radius 5, I need a sector with a central angle of 60 degrees, and I need to find what the arc length is, and just for fun, what the perimeter is, and the area of that sector. Now, arc length is the proportion or the portion of the overall circle that we have with its circumference there. So I need r theta with theta in radians. So I convert 60 degrees into radians, which is going to be, hopefully we'll all agree, pi over 3 radians. And I multiply that by 5 to get my arc length. And also, if you wanted perimeter, right, recognizing that for these pizza wedges, I've got my arc length plus radius to get the overall perimeter. I would just add 2r to that, or 5 pi over 3 plus 10. Not really terribly important, but just kind of for completeness sake. And then lastly, sector area, I use this formula. I have to again convert to radians, or just reuse the radian measure I found earlier, and I'll end up with 25 pi over 6 square units. And just as a quick check here to round us out, this should make some amount of sense. Right? 60 degrees is 1/6 of 360 degrees. It's 1/6 of the entire circle. So I need 1/6 of the overall circumference, and I need 1/6 of the overall area. The overall circumference of a circle radius 5 is going to be 10 pi. I cut 10 pi in 6, I get 5 pi over 3. The overall area is going to be, pi r squared, so this should be 25 pi for the overall area. So my sector area, being 1/6 of that, is going to be 25 pi over 6. And that's how we do it. So there is one immediate application. The next and final application I want us to look at here, I'm just going to kind of present. We'll work a few problems to this effect in this class. This just, for those of you taking engineering, mechanical specifically, this is something that you will learn to live with. But I'll just get you exposed to it in this class. Right? Knowing that S equal r theta, right? There is an established relationship between radius and angular distance. That's a direct proportion. So the rate at which they change has to also be directly proportional. Or in other words, velocity at any point as we move on a circle is equal to the radius times the angular speed, or how quickly we're rotating. And once again, right, velocity is in, meters per second, or distance per time unit, distance unit per time unit. Radius is just your distance unit, so omega has to be unitless over time. So once again, angular speed has to be in radians per second, or radians per time unit. So once again, whenever we're working with linear speed or angular speed, once again, we're going to have to work in radian mode. So here's a couple of instances where we have to do it. Even if degrees make more sense to us from a sketching perspective, if we understand what 115 degrees looks like way better than what 2 radians looks like, that's understandable. I'm in that same position. But there are times where we have to work in radians mode, and those are for very real, very physical applications. For instance, this equation right here, and we'll show this in class, can be used to answer the question, how fast am I going right now? Sitting where I'm sitting, what is my speed? And by that I mean, no, not 0. Right? Relative to the Earth, yeah, sure, 0. But relative to the center of the Earth, I am sitting on a point on the radius of the Earth, and I am moving with an angular speed of 1 full revolution every 24 hours. I have some omega, I have some r, I have some velocity based on that. So we'll find out in class how fast we are going right now. So I hope you look forward to that, because we have now reached the end. We have a couple of quick application problems to look at in class, but we have reached the end of this first unit. We've got now trigonometric functions defined, transformations, graphs, we've got inverse trig defined, we have general rotation defined, we have applications of angle measure defined. We have all the groundwork laid out to move forward in this course. So I hope this has been a productive use of class time and, of course, home time. So let me know how that goes. And also, I'll see you in class. We'll get this wrapped up, and then we'll take our first test. Should be fun. Okay, maybe not, but it should happen. So you guys have a good one.